Hey, this lesson is an introductory lesson to thermodynamics. So we began this unit by actually doing what's called a calorimetry lab. So we were determining the calorie content of a food item, and we really didn't discuss how this actually works yet. So I'm going to be giving you guys a little bit of a background now on how we actually calculate calories, what a calorie is, etc. Okay, so calorie is one of the ways that we measure heat. So it is a unit of energy. So heat and energy are going to be used interchangeably. They are the same thing. And so the definition of a calorie is the amount of heat or the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So 1 calorie equals a gram degree Celsius. So we're actually going to write that as 1 calorie per gram Celsius. And then we discussed that the energy stored in food is a calorie with a capital C, which is actually a kilocalorie in terms of chemistry calories. Okay, so 1 food calorie equals 1,000 chemistry calories. Okay, equals 1 kilocalorie. So in other words, hopefully you can see this when I write this on the board. If we have, say, a soda, like a Coke, and maybe that can is, I don't know, 180 calories. That's our food calories. We could also say that that is 180 kilocalories. Okay, but in terms of chemistry calories, which is what we'll be working with in this class, that'd be 180,000 chemistry calories. All right, and then we also have another unit of energy that we'll be using, and that is a joule. And 1 chemistry calorie equals 4.184 joules. Okay, that'll be a really easy one to convert between. Okay, so a calorimeter is an insulated device to measure temperature changes. So your fancy calorimeter that you used in this lab was made up of a soda can. And it can determine what's called enthalpy changes or heat of reactions. We'll talk more about enthalpy in the second lesson. Okay, so terms you've probably heard before in previous science classes is endothermic and exothermic. So an exothermic process releases heat, so the temperature of the surroundings increases. And in an endothermic process, heat is absorbed, so the temperature of the surroundings decreases. So we usually identify what our actual system is in the surroundings in a thermodynamic problem. Okay, and we'll get more into endothermic and exothermic in the second lesson. All right, so in order for us to figure out how many calories were in the food, we needed to know what the specific heat of water is. So a calorie was the energy required to raise 1 gram of water by 1 degree Celsius. So similarly, specific heat is the amount of heat required to raise 1 gram of a substance by 1 degree Celsius. So we were able to calculate the calories in the food because we know what the specific heat of water is. Okay, so this is a physical property, and the specific heat of water is 4.184 joules per gram Celsius, or 1 calorie per gram Celsius, which is the value we used yesterday. So remember, 1 chemistry calorie equals 4.184 joules per gram Celsius. So we could also write the specific heat of water as 1 calorie per gram Celsius. Okay, they're just calories and joules are 2 different units of energy. Okay, so we said that it is the amount of heat, okay, so that's why we use the unit of heat, required to raise 1 gram of a substance by 1 degree Celsius. Okay, so that's why it's calories per gram Celsius or joules per gram Celsius. We could also measure it in joules per gram Kelvin or calories per gram Kelvin. Okay, we have multiple units that could be used here. All right, and if we look at the specific heat of water compared to iron, you'll see that the specific heat of iron is much lower. So it's 0.449 joules per gram Celsius. So it would take 0.449 joules to raise 1 gram of iron by 1 degree Celsius. Okay, so these values are going to come from a table. We could also calculate them. We'll actually determine the specific heat of a metal in our laboratory in this unit. Okay, so water has a high heat capacity. So we said that the specific heat of water was 4.184 joules per gram Celsius. Okay, so that means that it's going to absorb a large quantity of heat with only a small increase in temperature. So it would take 4.184 joules to raise 1 gram of water 1 degree Celsius. Okay, compared to iron, which has a specific heat of, what was that, 0.449? So, sorry, it shows a bad color for this slide. So 4.184 joules per gram Celsius versus 0.449 joules per gram Celsius. Okay, so in one case we would need about 4 joules of energy to raise it by 1 degree Celsius. And for our metal, we only need about a half of a joule to raise it by raise 1 gram by 1 degree Celsius. So water is going to absorb a large amount of heat with a small increase in temperature. So if you think about when you are going to boil water, you can keep that water on the stove for a long time. It's going to keep absorbing energy. If you were to touch that pot, you know that pot would be really, really hot, but the water wouldn't quite be as hot because it needs to absorb a lot of energy to change the temperature. It can also give up a large quantity of heat with only a small decrease in temperature. So it would have to lose 4.184 joules in order for it to decrease 1 gram by 1 degree Celsius. So if you think about when you heat up something like soup, it's going to take a long time for it to cool down versus maybe some other food that doesn't have a high water content. Metals have a low heat capacity. So it only takes a little bit of energy to have a temperature change. So if you think about if it's a really, really, really hot day and you go ahead and you grab your seatbelt when you hop in the car, you're going to notice that the seatbelt is very, very hot, a lot hotter than it is outside. So it only needed to absorb a little bit of energy, just a half a joule of energy before we raised that by a degree Celsius. It can also have a small amount of heat lost with a large temperature change. So if you think about back when you were a kid and you went to the park and you hopped on the swing set early in the morning when it's real cold outside, and when you grab those chains on the swing, you'll notice that they're very, very cold, colder than it is outside. So we are losing a little bit, we only need to lose a little bit of energy to have a temperature change. Okay, so real quick, I think it's important that we discuss the difference. Oh, whoops, sorry. First, let's look at our equation that we were using for specific heat, and then we'll talk about what the difference is between heat and temperature. Sorry, I thought that was the next slide. So we've got our equation. So Q equals Cm delta T, or I usually say it as MC delta T. Q equals MCAT. That's how I remember it. So Q is going to represent heat released or absorbed. So if heat is released in the process, it's going to be a negative value. If heat is absorbed, it's going to be positive. So it is possible to have a negative heat value or a positive value. And C, this is CP. We actually are only going to work with CP in this class. So you might just see it written as just C. Okay, without that little subscript, we are not going to deal with Cm in this class. M is going to represent the mass, and delta T, So delta anything means change in. So it would be a measure of how much the temperature changed. So we always do the final temperature minus the initial temperature. It's important that you know that it's the final minus the initial, so the temperature we end with minus the temperature that we start with, because it is possible to get a negative value here. Okay, we can have the temperature go up or we can have the temperature go down. So it's not always going to be the larger number minus the smaller number. Okay, and the units we measure those in, again, for heat, we're going to measure that in joules or calories, so you need to be able to recognize that. And specific heat, we can have joules per gram Kelvin, joules per gram Celsius, calories per gram Celsius, calories per gram Kelvin. So it's going to be some energy unit over grams and a temperature unit. Okay. Actually, we could also do joules per mole Kelvin. So we've got energy, the amount of the substance, and the temperature. But basically, you'll recognize the specific heat because you'll see energy, amount of substance, and temperature, because specific heat is the amount of energy required to raise some amount of substance by some temperature unit. So it's important that you know the definition of that so you're able to recognize these variables when you're going to plug them into an equation. All right, and then mass, of course, will be measured in grams. We could technically also plug in moles for this. You guys will see some examples with that on your worksheet. It's actually really, really easy. We just want to make sure that our units match up with our specific heat units. And then temperature can actually be measured in Kelvin or Celsius. So in the previous unit for gas laws, we were unable to plug in Celsius values for temperature, but now you can. Okay, so now let's just talk real quickly about the difference between temperature versus heat. Okay, so they are not the same thing, although we do use these terms somewhat interchangeably in everyday life. But a temperature is the measure of the average kinetic energy, so energy of motion. And okay, we know that Kelvin equals Celsius plus 273. Okay, versus heat is the amount of energy that flows between matter. Okay, so when energy is being transferred. It flows from matter of higher temperature to matter of a lower temperature. Okay, so this is energy exchange versus temperature measures the average kinetic energy of the molecules in motion. Okay, so hot molecules move quickly into areas of slower moving cold molecules. So we're going to have things move from an area of higher temperature to lower temperature. And the idea is that we kind of things want to be equilibrated. They want to be equal. So if an area is colder, if we move heat into that area, we can equal them out. Okay, a little bit more on temperature. So in chemistry, we are never going to use Fahrenheit. Fahrenheit is the F word. We always are going to be using Celsius or Kelvin. And the conversion between Celsius and Kelvin is very easy. You guys have worked with it before, so we're just going to take the temperature in Celsius and add 273 to get Kelvin, or the temperature in Kelvin, subtract 273 to get Celsius. You'll see over on the right-hand side that we've got much more complicated formulas to convert between Celsius and Fahrenheit, which is unfortunate when you travel. So I know that I had to quickly memorize these so that I could discuss the weather with people, since that's what we do. Or if I was looking for the weather that morning, a lot of the temperatures don't mean a whole lot to me when I see them in Celsius. So you want to know how to do those conversions if you are going to be traveling to Europe or Australia or pretty much anywhere in the world. They don't use Fahrenheit. Okay. Another touch on heat. So again, this is the transfer of energy from a hotter object to a colder object. So I'm just reiterating what we said on the last slide. We're using a symbol of Q for heat. for these problems. So you guys saw the equation Q equals mc delta T. It's important that you know that particles are always, always, always moving. The only time that particles are not moving is at absolute zero or 0 Kelvin. So even if you are looking at the desk you are sitting at, the particles are moving in that desk as well. Okay, remember that things are made up of atoms, which we've got electrons that are moving around. And then I'll demo for you guys in class when you heat things up, the molecules do move faster. So kind of a joke here, close the window, you're letting the cold in. Nope, you wouldn't be letting the cold in. The heat would actually be going out. Okay, sample problem. If 75 grams of iron with a specific heat of 0.449 joules per gram Celsius is heated from 274 Kelvin to 314 Kelvin, what is the amount of heat that is absorbed? Okay, so the first step is to outline what information we know. So we know that we are working with specific heat, so the equation was Q equals mc delta T. So I'm going to outline those variables. All right, so let's see, we've got 75 grams, which would be our mass. It's heated from 274 Kelvin to 314 Kelvin. So like if I was going from Covina to Glendora, my starting place would be Covina, my ending place would be Glendora. So let's break that down into final and initial. So final is 314 because I was going from 274 to 314. And the initial 274. And it gives you the specific heat, which is 0.449 joules per gram Kelvin. Okay. And I can see that my temperature units all match up. I've got Kelvin, Kelvin, Kelvin. I've got grams and grams. And it looks that my answer will end up being in joules. That's the energy unit that we're using here. So we're just going to plug that information in to the equation. So 75 grams, 0.449 joules. Actually, let me write it like this. Joules per gram Celsius. Oops, excuse me, Kelvin. And we're going to plug in delta T. So we need to do the final temperature minus the initial temperature to get the change in temperature. So 314 minus 274, we'll get 40 Kelvin. Okay, so we're just going to multiply those values, but I do want to point out that the units are going to cancel out. Okay, you don't have to plug them in with the units. So that's 75 times 0.449 times 40, and you will get 1347 joules as your answer.